torsion coefficient links here. A torsion spring is a spring that works by torsion or twisting, that is, a flexible, elastic object that stores mechanical energy when it is twisted. When it is twisted, it exerts a force in the opposite direction, proportional to the amount it is twisted. There are two types. A torsion bar is a straight bar of metal or rubber that is subjected to twisting about its axis by torque applied at its ends. A more delicate form used in sensitive instruments, called a torsion fiber, consists of a fiber of silk, glass, or quartz under tension, that is twisted about its axis. The other type, a helical torsion spring, is a metal rod or wire in the shape of a helix that is subjected to twisting about the axis of the coil by sideways forces applied to its ends, twisting the coil tighter. This terminology can be confusing because in a helical torsion spring the forces acting on the wire are actually bending stresses, not torsional stresses. Uses. Some familiar examples of uses of the strong, helical torsion springs that operate clothespins and traditional spring-loaded bar-type mousetraps. Other uses are in the large coil torsion springs used to counterbalance the weight of garage doors, and a similar system is used to assist in opening the trunk cover on some sedans. Small, coil torsion springs are often used to operate pop-up doors found on small consumer goods like digital cameras and compact disc players. Other more specific uses. A torsion bar suspension is a thick, steel torsion bar spring attached to the body of a vehicle at one end and to a lever arm which attaches to the axle of the wheel at the other. It absorbs road shocks as the wheel goes over bumps and rough road surfaces, cushioning the ride for the passengers. Torsion bar suspensions are used in many modern cars and trucks, as well as military vehicles. The sway bar used in many vehicle suspension systems also uses the torsion spring principle. The torsion pendulum used in torsion pendulum clocks is a wheel-shaped weight suspended from its center by a wire torsion spring. The weight rotates about the axis of the spring, twisting it, instead of swinging like an ordinary pendulum. The force of the spring reverses the direction of rotation, so the wheel oscillates back and forth, driven at the top by the clock's gears. The torsion catapult, a mangonel, is a medieval siege engine invented by the ancient Greeks. It uses a torsion spring consisting of twisted ropes to swing an arm that throws a heavy missile at the enemy with great force. The balance spring, a hairspring in mechanical watches, is a fine, spiral-shaped torsion spring that pushes the balance wheel back toward its center position as it rotates back and forth. The balance wheel and spring function similarly to the torsion pendulum above in keeping time for the watch. The D'Arsonval movement used in mechanical pointer-type meters to measure electric current is a type of torsion balance. A coil of wire attached to the pointer twists in a magnetic field against the resistance of a torsion spring. Hooke's law ensures that the angle of the pointer is proportional to the current. A DMG, digital micromirror device chip, is at the heart of many video projectors. It uses hundreds of thousands of tiny mirrors on tiny torsion springs fabricated on a silicon surface to reflect light onto the screen, forming the image. Torsion balance. The torsion balance, also called torsion pendulum, is a scientific apparatus for measuring very weak forces, usually credited to Charles Augustin de Coulomb, who invented it in 1777, but independently invented by John Mitchell sometime before 1783. Its most well-known uses were by Coulomb to measure the electrostatic force between charges to establish Coulomb's law, and by Henry Cavendish in 1798 in the Cavendish experiment to measure the gravitational force between two masses to calculate the density of the Earth, leading later to a value for the gravitational constant. The torsion balance consists of a bar suspended from its middle by a thin fiber. The fiber acts as a very weak torsion spring. If an unknown force is applied at right angles to the ends of the bar will rotate, twisting the fiber, until it reaches an equilibrium where the twisting force or torque of the fiber balances the applied force. Then the magnitude of the force is proportional to the angle of the bar. The sensitivity of the instrument comes from the weak spring constant of the fiber, so a very weak force causes a large rotation of the bar. In Coulomb's experiment, the torsion balance was an insulating rod with a metal-coated ball attached to one end, suspended by a silk thread. The ball was charged with a known charge of static electricity, and a second charged ball of the same polarity was brought near it. The two charged balls repelled one another, twisting the fiber through a certain angle, which could be read from a scale on the instrument. By knowing how much force it took to twist the fiber through a given angle, Coulomb was able to calculate the force between the balls, determining the force for different charges and different separations between the balls. He showed that it followed an inverse square proportionality law, now known as Coulomb's law. To measure the unknown force, the spring constant of the torsion fiber must first be known. This is difficult to measure directly because of the smallness of the force. Cavendish accomplished this by a method widely used since, measuring the resonant vibration period of the balance. If the free balance is twisted and released, it will oscillate slowly clockwise and counterclockwise as a harmonic oscillator, at a frequency that depends on the moment of inertia of the beam and the elasticity of the fiber. Since the inertia of the beam can be found from its mass, the spring constant can be calculated. Coulomb first developed the theory of torsion fibers and the torsion balance in his 1785 memoir, Recherches théoriques et expérimentales sur la force de torsion et sur l'élasticité des fils de métal and amp. C. This led to its use in other scientific instruments, such as galvanometers, and a Nichols radiometer which measured the radiation pressure of light. In the early 1900s, gravitational torsion balances were used in petroleum prospecting. Today, torsion balances are still used in physics experiments. In 1987, gravity researcher A.H. Cook wrote, "The most important advance in experiments on gravitation and other delicate measurements was the introduction of the torsion balance by Mitchell and its use by Cavendish. It has been the basis of all the most significant experiments on gravitation ever since." Bibliography: Cavendish H. Experiments to determine the density of the Earth in Mackenzie A.S. Scientific Memoirs, Volume 9. The Laws of Gravitation, American Book Co. pp. 59-105. McCormack, R. Jung Nichol, C. Cavendish, American Philosophical Society, pp. 335-344, ISBN 0871692201. Gray, Andrew. The Theory and Practice of Absolute Measurements in Electricity and Magnetism, Volume 1, Macmillan, pp. 254-260. Detailed account of Coulomb's experiment. Charles Augustin de Coulomb. Biography, Chemistry Department, Hebrew Univ. of Jerusalem. Archived from the original on 6 August 2009. Retrieved August 2, 2007. Shows pictures of the Coulomb torsion balance, and describes Coulomb's contributions to torsion technology. Nichols, E.F. Hull, F. The Pressure Due to Radiation. The Astrophysical Journal, 17, 315-351. Bibco, 1903 APJ. 17, 315 N. DO on 10.1086, 141,035. Describes the Nichols radiometer, torsion balance, Virtual Geoscience Center, Society of Exploration Geophysicists, retrieved 4 August 2007. Description of how torsion balances were used in petroleum prospecting, with pictures of a 1902 instrument. Charles Augustin de Coulomb, Encyclopaedia Britannica, 9th ed. 6, Wernicke, 1907, p. 452.